Make me more ribs. Make me more ribs. Oh, you were good. Hey, folks, I'm waiting for you. So today we're going to talk about how we show energy changes. We're going to do an example here now, and then we'll have a worksheet to work on. And then ultimately there is a practice quiz. So here is how this works. There's a couple of different types of ways to show this that we're going to talk about. The first one is called energy bar charts. These are my favorite. And they look like this. What's that look like? We actually call them that. LOL diagram is kind of their other name because they look like that. Okay? So these two right here are something that you'll recognize. We did this before, right? Right? Does that look familiar? It's somewhere else in your notes. Okay. This right here, the circle in the middle, is where we draw the thing that we're talking about, which we call our system. So let's do something really simple here right now. Let's make some hot chocolate. What? It's the same as what was on the graph that you did the other day. ETH for thermal energy, EPH for phase energy, and ECH for chemical energy. It's the same on both L's. It's the same. It'll be the same every time you ever see a little graph like this. Does that help? Yeah. All right. Thanks for asking. All right, so let's make some hot chocolate. You guys ready? Yeah. So there's different ways to get hot water. Some people just get it from their coffee machine. I prefer to get it from either the little electric kettle sitting on my counter, or sometimes you just stick it in the microwave. Today we're going to do it the microwave way just because it's really simple and easy to understand. So are you ready? Draw your hot chocolate in here. I'm even going to give my little mug a handle. All right? So, how do you make this hot chocolate? What do? Add water. Where do you get your water from, by the way? Probably the faucet. So let's talk about this water that we start with. The water that we start with, how hot is it? Like room temperature. Is that cold? Is it cold? So does it have some thermal energy? Yes. I'm going to say, just to make things really easy, I'm going to say that it has like whatever I want to call 2 bars of thermal energy. Is that a magic number?
Wait, I'm curious.
What?
So like you draw like the bar and then like what are the dots inside?
Just to show like that it's too high. Like on your paper, you can use just like your lines of your paper.
Oh, okay.
Does that make sense?
Yeah.
This is my way of making cheap graph paper. Okay.
I was just seeing what it's mean like.
Yeah, no, that's all it means. And then your phase energy. What's phase energy? Flip back in your notes and remember, what is phase energy? Energy that separates particles from each other. He stole it from you, didn't he? So if you have energy that separates particles from each other, do liquids have space between the particles? Yes, but just a little bit, right? So we're going to talk about phase energy for a liquid as being 2 bars high, okay? And make yourself a note over here. Liquid equals 2 bars of phase energy. Okay? Just because it makes things really simple that way. I've actually heard long arguments about how many bars that you should give these things, but when it comes down to it at the end of the day, it doesn't really matter except to say that you can compare it from the beginning to the end. Does that make sense? So if you just keep liquids as always being 2 bars, it'll always work. Sound good? All right. Now, what are we going to do to this hot chocolate cup? Stick it in the microwave. And what is the microwave going to do to it?
Warm it up.
Warm it up. What does chemistry speak for warm it up? Heat. What does that mean to the particles? Make the particles go faster. And what do we have to do to make particles go faster? Add heat, which is what? It's energy, right? What kind of energy is it? Thermal energy, right? So we're just going to add some energy. There we go. That's my energy. You like my beautiful drawing of energy? It's a box. All right? Now, at the end, after our hot chocolate is in the microwave, what are we going to do? How much thermal energy are we going to have now? We had 2. Now we have, how many is that? 1. So how many do we have now?
3.
Right? What about phase energy? How much phase energy do we have? Phase energy separates the particles from each other.
I'd say keep it 2.
Well, do we still have a liquid?
Yeah.
So it's still going to be 2. Does that make sense?
Yeah.
So do you see here that we started out with 2 over here. We added 1. You don't have to color code these. I'm just doing it so you can see it a little bit better. We added 1, and oh, look, there it is right there. Does that make sense?
Yeah.
Direct correlation right there. Sound good?
Yeah.
All right. So the next thing here is that I have a worksheet for us. You're going to get to do some of these. Okay, so first off, this is number 1 on your worksheet. Shh, hey, come on. This is number 1 on your worksheet. I'm going to do it like super, super quick. Okay? You have to have some thermal energy. Let's just say that's 2. You have some phase energy. What are you doing here? You're cooling off your coffee, right? Right? So this one, energy goes out. I'm going to make just 1 bar go out, but if you picked a different number of bars, it probably doesn't matter. And what goes out is what? Thermal energy or phase energy?
Thermal.
Thermal. So I drew this wrong. This should be up just like that. Make sense? Cool? Because this one right here is that. Wait a minute. I'm still messing this up, you guys. I'm so sorry. This one right here is this one right here. So that one went there and out. Cool? Shh. All right. Now, 2 things that we're going to add to this. We're going to add another type of energy diagram here. This is just called an energy graph. Okay? And I don't have a lot of room here, so I'm just going to kind of squish this in. This one, we just graph energy over time. Okay? Now, look at how this energy for this hot chocolate one changed. It started out relatively low, and then what? It went in, so it goes up. Right? Yes. Make sense? So this is how we would draw this one. Now, is this a simplified idea? Because obviously if you leave your hot chocolate sitting out here, it's going to get cold again? Yeah. Very simplified, okay? But this is just the simplified energy and time graph. How would we do this one? Do it. Do it real fast and look up when you think you've got it. The next thing to add to this, and this is where you probably want to put this in your notebook and not on this paper because you want to be able to find this later. There's two terms that we're going to discuss. You've probably heard these. I'm going to write them both. Leave yourself a couple of blank lines underneath each one. Have you heard? I wrote that one really small. Isn't that funny? Have you heard of these before?
Yeah.
Let's do a little bit of English here. You ready? What does therm mean?
Heat. Inside heat.
Means
outside
heat. It just means heat. What does endo mean?
Outside. Wait, no. Inside.
Josh is on it this time.
I think it's like inside.
I like to think of this one as meaning into because in my brain, into sounds like endo. Maybe that's a stretch. I don't know. And exo, what's exo mean?
Outside.
Exterior.
Outside, yeah. How about the word exit?
Gone, leave.
Right? So kind of the same when we talk about parts of a word and how words derive from Latin and Greek. Those are how those go. So, endothermic means energy does what? What do you think?
Enters.
Energy enters or goes in. Sound good? Exothermic means what? Okay, now listen to this very carefully because there's one thing that sometimes gets confusing about these two terms. Right now, we're dealing with these very simple problems where it's just a simple matter of warming up or cooling down. Does that make sense? Okay. When it's simple like this, this means if energy goes in, what does it do? Does it warm up or cool down?
Warm up.
Or talk about the temperature, right? Temp goes up. All right? But please write this in parentheses. We're going to revisit this later when we start doing some that are a little bit more complicated. And this idea is going to end up being complicated. Does that make sense? So maybe you want to even put yourself a little note in here right now saying this works when things are simple. Okay? Exothermic, if energy exits or goes out, what does that mean for the temperature?
Goes down.
All right? So those things right there are going to end up changing a little bit later. But this part right here is what will always, always work. The idea of energy entering, energy going in, energy coming out. Sometimes that's going to end up getting mixed up with temperature in a way that's going to be confusing. But for now, we're doing simple ones, so they always go together. Can you trust me on that for now? All right. Last thing before you go to lunch, I want you to label number 1, 2, and 3 on your worksheet as one of the two of those. And I want you to draw the energy graph for the other two. Ready, go.